Okay, so what does it have to do with atoms? Well, when atoms or molecules absorb energy, the energy is often released as light. We see this in fireworks. We see this in neon lights. We see this in fluorescent lights. Each element emits a characteristic color of light. So here we have 3 tubes. This has got mercury in it, and helium, and hydrogen. And the color that we see depends on the element that's present. Fireworks are different colors because what's exploding has different elements in it. This neon light literally has neon gas inside of a glass tube, and you pass electricity through it, and it glows that really, really bright orange color. If we take the light emitted from one of these things and pass it through a prism, instead of seeing a spectrum of a rainbow, we're going to see a series of lines, just the particular wavelengths that are emitted by that atom or molecule. It's called an emission spectrum. And we can use this to identify an element. It's much like a fingerprint or a barcode. And this cannot be explained by classical physics. So this is what we're talking about. You take this hydrogen lamp, and it's giving off this pinkish color, and you pass that through a slit so you can focus it and pass it through a prism. And instead of seeing a solid rainbow, like white light would give you this solid rainbow, what you're going to see is 3 lines and a bunch of black stuff. You're going to see a purple line and kind of this blue line and a red line. Because the hydrogen only gives off those particular energies of light. Helium would look like this. Barium looks like this. And so these are emission spectra. You can also look at absorption spectra, but here's oxygen and here's neon. And so we see a different pattern of lines, and it looks a little bit like a barcode, right? I got ahead of myself. This is emission versus absorption. So this is an emission spectrum for mercury, and this is an absorption. And so you can also shine light on it and see what frequencies or what energies are absorbed. And so then you see black spot or black lines, the same place you saw bright lines. Yes?
So each element is going to give off a different wavelength of one of those colors?
They're going to give off a different combination of wavelengths. So each line is a wavelength, a different wavelength. And so mercury does all of these lines, these bright spots here. So there's 2 yellow ones here, and there's an orange one here, and there's some over here. There's a bunch of different lines. And that pattern of lines at those particular wavelengths is characteristic of mercury. You can do flame tests. You stick sodium in a flame, and you get this very bright yellow-orange color. Potassium gives a purple flame, lithium gives a red flame, barium gives kind of a greenish flame. The colors that we're seeing, the atoms are getting excited by the heat of the flame, and then they release that energy as light, and we see it as different colors because it's a different combination of wavelengths. So a guy named Johannes Rydberg, back in the 1800s, analyzed many atomic spectra and found that they could be described with an equation that involved an inverse square of integers. Now this is based on just looking at the numbers and trying to find an equation that matches the numbers. There's no understanding or explanation of why. It's just saying, I came up with this equation that matches up with all of this stuff. It's just, an accomplishment, but it doesn't really give us any insight into what's going on here. But this is his equation. That 1 over the wavelength equals a constant times 1 over an integer squared minus 1 over another integer squared. And he could use that to find all of these different wavelengths. So Rutherford's nuclear model of the atom has a tiny dense center called the nucleus. The nucleus is essentially the entire mass of the atom. The nucleus is positively charged. The amount of positive charge in the nucleus balances the negative charge of the electrons outside the nucleus. This is review. The electrons then move around in the empty space of the atom surrounding the nucleus, and this chapter is about what are the electrons doing in that empty space. So electrons are moving charged particles. And according to classical physics, if you have a moving charged particle, it gives off energy. And so then electrons should be constantly giving off energy, and atoms should glow, right? They should just be giving off energy all the time. That would also mean that the electrons, because they're always losing energy, eventually would run out of energy and they would crash into the nucleus. The atom would collapse, but it doesn't do that. So the nuclear model of the atom doesn't explain what structural changes occur when the atom gains or loses energy. So Bohr, Niels Bohr, guy whose quote was at the beginning of the chapter, developed a model of the atom to explain how the structure of the atom changes when it absorbs energy. So his model is that the atom is like the solar system. We have electrons traveling around the nucleus in circular orbits. So the nucleus is like the sun, and the electrons are like planets orbiting the sun, right? The orbits exist at only specific fixed distances from the nucleus. You can only have, you can be in this orbit or you can be in this orbit. You can't go in between. So the energy of each orbit is fixed. We say that's quantized. The amount of energy in the atom is related to the electron's position in the atom. So quantized means that only specific values are allowed. So quantized versus continuous, I don't think I've got a slide really. I think I just remember to talk about it. If you think about stairs versus a ramp, and how high above the ground are you on the second step, or the third step, or the fourth step, you can only choose one of the steps to stand on, right? So let me draw a picture. Let's, so here we have a ramp, and here we have a set of stairs. Well, I lost the first step, that's okay. So if I'm on the stairs, I can be on this stair or this stair or that stair. And let's say this is, 1 foot and this is 2 feet and this is 3 feet tall, right? Can I stand at 2.5 feet above the ground? No, I can't. But on the ramp is continuous. It goes from 0 all the way up to 3. And so you can be anywhere along there. You could be at 3 feet, you could be at just a smidge less, you could be at 2 feet, you could be at 1.5 feet, you could be anywhere. This is continuous. And this is quantized. And there are lots of things in everyday life that are quantized. Our monetary system is quantized. Paper money, there's a $1 bill, the lesser known $2 bill, $5 bill, 10, 20, 50, 100. There's no $7 bill. Can you have $7? Sure, but you need a 5 and a 2, or a 5 and 2 ones, or 7 ones, right? There's no $7 bill. School is quantized. You're in first grade, you're in second grade. You can't be in 2.5 grade, right? There's no 2.5 grade class. You're in first or second or third. Guitars are quantized. They have frets. And you put your finger on the string and it touches the fret and you have a distinct note. And you can put your finger there or you can move your finger to the next one, but you can't go in between. A violin is continuous. There's no frets and you can move your finger all along that, and so you can get all kinds of just screechy, terrible sounds. I played the violin as a kid. Ugh. lots of different sounds that you can get. Okay, so there are lots of different examples of quantized versus continuous. Let's get back to where I am. Okay. So these orbits are quantized. And so Bohr's idea here was, so this is for the hydrogen atom. So here you've got an electron, and it's maybe in this orbit, and then you hit it with a bunch of electricity or energy, and you can cause the electron to jump to a higher energy orbit. That's not stable, and so eventually it's going to drop down to a lower energy orbit. And when it does, it will release that energy, because you can't create or destroy energy. So if you put energy in, the energy has to come back out again sometime. So when it jumps from the fifth orbit to the second orbit, it releases energy corresponding to 434 nanometers of light, so violet light. When it goes from the fourth level to the second level, it gives off this blue-green light. And from the third to the second, it gives off the red light. This is a longer wavelength that's lower energy. This is a shorter wavelength that's higher energy. So the emitted radiation is a photon of light, and the light has a different amount of energy. And so because there are only fixed transitions possible, we only see particular colors of light. Anybody have any questions? Does it make some sense? So it can go from here to here. It can go from here to here. It can go from 3 to 2. Now, other transitions are possible. You could go from 5 all the way down to 1, but that's more energy than the violet, and it's beyond the visible region, and so we don't see it. It exists. There's light coming off, electromagnetic radiation coming off, but we can't see it. And transitions like 2 to 1 is going to be a smaller amount of energy, and so that's going to be lower than the red, lower in energy, and we can't see it. So these are the three transitions that fall within the visible region of the spectrum. Yeah.
So if that one electron goes to like where the violet light would be, would it show those other two lights because it comes back to their like electron circle, I guess, or would it only show that violet light?
It would only show violet. So this one, it would make one jump from here to here, and that would give violet light. It could go from here to here, and then it could go down, go through each orbit. But again, these transitions are not a transition that we can see. And so this light is coming from electrons going from 5 to 2. This one is coming from electrons going from 4 directly to 2. So we get a photon of light for each electron transition. The electron is never between those orbits. It goes from one to another without going in between. And this is where we get into the quantum stuff, and you're like, but that's not possible. Because when you go up the stairs, are you instantly from one step to the next? No, because in the process of going up the stairs, you're elevating your body, and so very, very briefly, you pass through other distances, right? Because we're real life regular things, and we obey regular rules of physics. This is called a quantum leap. It goes from one state to another state without going in between. The energy of the photon is the energy difference between those two states, and from the wavelengths we can actually calculate the energies. So the Bohr model is important, has great historical and conceptual importance, but unfortunately it only worked for the hydrogen atom. Yeah. So great, it works for hydrogen, you can calculate all kinds of stuff and do cool things, but it only worked for hydrogen. So it's not very useful because most of the other elements are not hydrogen, right? So it was ultimately replaced by quantum mechanics. But we still teach you about this because The Bohr model is much easier to understand conceptually. And we can think of the atom being like the Bohr model, even as we recognize that it isn't.